Okay, I think I'm ready to get started. Hello, wonderful people of the internet. Welcome back to another live lecture. Also, welcome, class 18S191 on computational thinking. Let me go ahead and check, make sure that I am live. I think I am. Wait, let me check. Yes, I'm good. Sorry about that. I had to make sure that all the OBS setting is good. Okay, so before continuing, I want to do some quick bookkeeping about Tuesday's past lecture. So, a lot of you guys might have noticed that we did not have a lecture that went up on Tuesday, or maybe we had a lecture and it went down really quickly. Truth be told, there was some technical difficulties to that lecture, but we're reworking the content both into the homework set this afternoon, which should be coming out this afternoon, and also into some of the lectures down the road. So that's where that will go. We do apologize for that. Just things happen, as we do things live and stuff like that. Now, obviously, if you guys have any questions, comments, concerns, ideas, anything like that, while we're doing this live lecture, please feel free to check the Discord link below. I won't be able to monitor the Discord directly, but I do have a Slack up on the side where I'll be looking at comments specifically from the other professors during this lecture. And so if there are any good questions, I would be really happy to talk about those as they come up. Okay, so what are we doing today? Today, we're going to be doing something that I'm going to be honest, some of you guys might have seen before, but if you've seen it, I hope you don't spoil it for those people who haven't seen it. So if you may have noticed in the last live lecture done by Dave, we kind of started doing this idea of random walking and stuff like this, eventually working our way into an SIR or an epidemic model. Now, I felt that this particular course has a very good understanding and conceptually we cover a lot of very important topics. But I thought one topic that we didn't really cover yet, and I really wanted to cover in this way because I think it's really cool and intuitive, were trees, graphs, and data structures like that. So I'm going to start today by first motivating trees, graphs, this type of stuff, explaining how they work, explaining how to traverse them, all this kind of stuff. And then after that, we're going to move into how we can extend them into an epidemic-like algorithm. Now, when I say epidemic-like, note that this is different than the epidemic models that you are typically used to seeing now on YouTube and through the news and stuff like this. The epidemic protocol that we'll be showing today is primarily about information flow across the network. That is to say, we have a bunch of people, they're interacting, and we're modeling how the disease spreads. So first, let's motivate graphs, explain why I think they're awesome, and then we'll move on to the next bit, which will be talking about SIR and all that kind of stuff. So quite frankly, all of the interesting algorithms that I can think of usually have some form of graph inside of them. We have galaxy simulations, color quantization, bucket fill, COVID cases, stuff like that. So if you aren't familiar with the color quantization and the bucket fill is what you see whenever you go to like an art application and you've got the little fill bucket and you try to fill in the circle. And color quantization is what you do to minimize the number of colors in an image before you actually store it in like a GIF or a PNG image or something like that. So basically, a lot of the really cool algorithms that I know about have something to do with graph and tree traversal. So because of that, I thought it was really important to just talk about it and maybe sit down together, me and you, and figure out how it works at a fundamental level. So let's start by talking about what exactly a graph is. Again, I don't mean to start too basic, but I feel like maybe you can never start too basic with this kind of stuff. So we're going to draw a single node here. This we'll define as a person, maybe. And this guy will be connected to some other person over here, right? And connected to some other person over here. The point is, I'm going to define a graph as basically any set of connected people, or abstracting it to any set of connected nodes, which I'll draw with, circles in here. Now, of course, we can connect them in any way we so choose. So I can create like a little bow tie here. Maybe this guy's connected over here. It doesn't really matter. The point is that this particular character is connected in some way to this character over here. Now, for the purposes of the start of this lecture, just to kind of get the ball rolling, I'm going to draw a very specific graph that a lot of people probably know. And that graph will be a binary tree. So the idea here is we start with a single element. And it extends left and right to an element here and an element here. Then it extends left and right again to here and here and here and here. Now, the way this works is we have a parent node up here, and then we have child nodes over here. I'm going to be abstracting this into like a full set of neighbors and stuff like that. So don't worry so much about the notation here. The point is that these guys are connected in some way. And I've got two rather interesting questions that I want to ask. First, how do we write this? What does this look like in code? And two, how exactly do we go about moving through this graph? How do we traverse the graph? Okay, so that's kind of where we're starting with. And again, please ask any questions you have. So what I'm going to do is close this and close that. Is I'm going to comment on something. Last live lecture, someone mentioned that my text was too small. So I'm going to be doing something today that I hope works out, but might not. And I'm going to be switching between these giant terminal screens so that you guys can see what's happening a bit better. This is a bit more complicated on my end, but I think it'll turn out a bit nicer. So I'm going to go ahead and start writing some code that creates our tree. So I'm going to start by using data structures, which is something we'll use later on. And then I'm going to include a set of tree helpers. Now, these are just things that will help me visualize the tree later on. Now what I'm going to do is create a mutable struct node. Inside of this, we'll have the set of neighbors, the set of connected nodes. And each one of these nodes will have an ID associated with it, which I'm casting onto an int64. You don't have to, but that's what I'm doing. And then I'm creating some sort of constructor here. Now, there are some quick questions about, is this actually the best way to store information inside of a tree? Probably not, but we'll get to that in a bit, so don't spoil it. Okay, so the next thing, oh, actually, I just realized I'm moving on to the next bit too early. So, sorry about that. Might have gone too quick. Okay. So, I don't know what's happening now. I don't know why it's just printing out E. So let's try that one again. I have no idea what just happened. Like, my entire terminal just died. So we're going to create what we just had, and then we're going to keep going. Okay. So this is literally all we need for creating a struct tree node. It's basically all we need to get started. So now I'm going to switch over to a Julia REPL, which should be this one here. And I'm just going to include this file. So include, one second. What did I call it? I called it tree? I'm having some technical difficulties today, guys. I apologize for that one. Okay, so let's just run to the right directory. Now let's try including again. There we go. Got it this time. Tree. I think I just call it tree.jl. And so this will include the data structures package and the file that we had over here. Once that's done, we will have some additional basically functions that I'd created to create a tree, which we'll set as the binary tree that we had before. So we'll do tree is going to be equal to, I'm just going to say create tree, and we're going to say 2. Let that run. Invalid character. I'm sorry I'm debugging stuff. I don't know what's going on here. I've never seen this error before, so I'm going to hope that it works the third time. Could not open file. Yep, I know why. Okay, so we're going to cd. Now we're going to try it again. If anybody, I don't understand what that error was, and I do apologize for that. So we're going to try it one more time. Could not open file. Invalid character near column 1. Was there some weird ASCII going on that I wasn't aware of? Oh, what? I'm not able to type. What is going on? I'm just gonna, I'm having some technical difficulties, guys, and I do apologize for that. But we can keep going nonetheless. I might just show the code, and then just keep going from there. Okay, so let's actually go back to our discussion that we had before. So like I said before, writing the tree is relatively straightforward. We just have the code that we had before with some sort of node. Inside of it, we have the set of a set of elements associated with it. A more important question, or rather another question that people have, is how do we move through the tree, right? And this is actually surprisingly more complicated than you might think. Because at first glance, you know, if we're trying to move through and see all of the elements in the tree, you'll probably start at element 1 up here, and then you'll move to 2 down here. But then we have an open question. Which way do you go from here? Do you go over this way, or do you go down this way, right? Because you could count. So it's 1, 2, 3, 4, 5, 6, 7. Or you could count 1, 2, 3, going all the way down, 4, 5, 6, 7. So what we have here is I just got a note from Dave about the issue, and I'll bring that up in a second. So what we have here is a basic breadth first search, and down here we have something called a depth first search. So the idea with the depth first search is that you just go as far down the tree as you can before moving to other nodes around the area. And the idea with the breadth first search is you go across the breadth of the tree this way. Now Dave just asked a question, can you open the source code? And I'm gonna show you why I don't think I can. Because for some reason it's in the repl.jl file 288, and I don't understand where that is. I can open up a new terminal, maybe? There's something really going screwy with this, so let me just close this terminal entirely, and let me make a new one. So give me just a second, guys. I have this screen on stream anyway, for just this case. Alright, so we're going to cd and projects. Give me just a second. Sorry about that, guys. Should be that one, I believe. Wait. Yeah, that one. All right. If this doesn't work, we'll see. Let's see that one. Okay. All right. So let's see if this works. I'm gonna run Julia again. What? I'm not sure what's happening, but like everything is. It's like just. What is happening? What is up with the AA there? Okay. Well, let's just try including something. Tree.jl could not open. Of course, I've got a CD. I'm sorry about the technical difficulties, guys. Here. Now we're going to include tree.jl. See if it works this time. I don't know. I don't know at all. Shashi sent me a message. My screen is off. Oh, sorry about that, guys. Thanks for that. So now my screen should be back on. I've included the tree. Give me a second. This might work. So now we're going to do tree is going to be equal to create tree. There. We have the tree. Let's see if this works. So we're going to try graph plot on the tree. Hopefully that worked. I'm so sorry about all of that issues, but that's okay. It happens. You know, we're doing it live. That happens. Let me fix something over here. Okay. So give that just a second to plot, and we should be good to go. That's great. Okay, so everything works now. I have no idea what was going on wrong before, but here we have our tree, and it is working as expected. So we have 1, 2, 3, 4, 5, 6, 7. So this is in the depth first scheme that we had before, counting like this. 1, 2, counting like this. 1, 2, 3, 4, 5, 6, 7. Okay, because of the technical difficulties, I'm going to have to speed up just a bit. Do apologize for that. But let's just keep going. Okay, so let's start with the depth first search, since we already have that drawn in the tree. And the idea is, if we do a depth first search of that tree, presumably, if we do that depth first search, we should count back 1, 2, 3, 4, 5, 6, 7, right? So I'm going to go ahead and move to this terminal, and we're just going to go ahead and write a very simple depth first search recursive scheme. Now, when I say it's simple if you understand recursion, and basically no one understands recursion. So, you know, it is what it is. We have depth first search recursion here, working on n, which I'm specifying of type node. And here I do something. For me, I'm just printing the identity of whatever element I'm on, but you could do anything here. And then basically I'm going through every single neighbor in our set of neighbors. Again, this would be the 2 children underneath, and I'm basically applying the function again. So again, the way this would work is that I start by calling the function here, it calls the function here, and then it calls the function here. So it just keeps going down the tree before it comes back up, and then calls the second half of the function on the other neighbor for this node. Again, so if I run this depth first search recursive on the tree, I now understand exactly what's happening. Okay, I now understand. So maybe we can solve the issue. Okay, so now if I do dfs, let me include the file. Could not ls. Did I write the file? Try it again. Let's do control. Oh man, this is gonna be rough. But I do understand what's happening now. Okay. Wow, okay, this is annoying. Okay, include tree. Hopefully includes, everything should work. We're just gonna go with it. All right, worst case scenario, it doesn't work, and we'll keep going. No one understands recursion. I see that in chat. Don't. All right. So I know what's happening. The issue is when I'm switching scenes, I'm actually pressing Control Alt something, which is putting an ASCII character into some of my terminals for some reason. So that's what's happening. I understand it now. So let me put this up, the embarrassing screen again. Let me refix this terminal, and now I just have to be wary of that and know that that's an issue coming forward. So, oh man. So now we're going to CD into projects. You guys can't see anything. Don't worry about it. I just promise it's happening on the side. Over here. And does that work? It looks like it is working. Great. So this should have the appropriate directory. And now we're just going to run Julia. And now we're just going to CD into the right directory, run include tree. And we should have everything working now. Oh, man. This is kind of fun, guys. I do apologize for the doing it live thing, but it is what it is. Also, I apologize way too much. How do I have a squared? Invalid syntax squared? Where'd that go? Probably here. Try it again. Near column 5. Okay. All right, let's go back. Where'd the ends come from? This is what I get for okay, there we have it. Now we're going to do tree. It's going to be equal to create tree. And then after that, we're going to run DFS recursive on the tree. And there we go, 1 through 7. Okay, let's just keep going now. I'm going to now start talking about something else. Oh, this is a wreck, but that's okay. So here's what we're going to do. I'm going to start talking a bit about different ways in which we can recurse through the tree. In principle, there are more than just the recursive way to go through with depth first search, right? We can also use stacks and queues, which is why I used the data structures package before. Now, what I'm going to do is I'm going to actually switch to another scene entirely, and I'm going to do something that might take a little bit of time, but I think is actually really important to help describing how stacks and queues work. So now you should be able to see my desk right here, which I can see, so it should be okay. What I'm going to do is I'm actually going to describe a stack and queue with actually a stack of cards. So here we have a stack of cards 1 through 7, right? What I'm going to do is I'm going to first describe what a stack is and how we can use it to do depth first search. So let's say we have 3 cards down, 1, 2, and 3. A stack is basically a data structure in which the very last element you put in is the very first element you take out. So you do that, and then this, and then that. A queue works the direct opposite way. If you put 3 cards in, let's do 1, 2, 3, the very first card that came in is the first that comes out. So that one, then this one, and then that one. I did a bad job of ordering that, but that's okay. So what I'm going to do now is I'm actually going to lay down the cards in a depth first fashion. So we're going to have 1, 2, 3, 4, 5, 6, and then 7. Now this actually really helped me when I was learning this for the first time, because essentially what you do is you take the first element, and this is actually the algorithm. You take the first element and you put it into some sort of stack, right? Now this is the only element in the stack. So what you do is you pop it, you remove it from the stack entirely, and then you put in its 2 children, which will be 5 and 2. And so then you take 2, you pop that, remove it from the stack, and put in its 2 children, which will be 4 and 3. After that, you put in 3 and 4, and then 5's left, so you pop its children, which will be 7 and 8. And then after that, you put 6 and 7 into the stack. I said 7 and 8. But thinking about it like this was actually really useful for me because you can just count. right? Okay, so another thing we can do is do the same thing for breadth first search. So we put these cards in the order that you would expect for breadth first search here. And the idea is you take the first element and you put it into a queue instead. Again, it's the only element in the queue. So you remove it and you put in its two children, 2 and 3. So these are the two elements in the queue. You then take 2 and you put in its two children, which in this case will be 5 and 4, 4 and 5. So they'll go under this guy. And this goes over here. 3 now goes in, 4 now goes in, and then 5 puts in its two children, which will be 6 and 7, and then 6 and 7 both go over here. I know that might have been a weird exercise to do, especially on a class like this, but I do think it's rather important to show, and I quite like showing that. So what I'm going to do is I'm now going to switch over to the code terminal, and we're going to see how this works. All right, so I'm going to switch over to this terminal over here, and we're just going to go ahead and write how to do this. So for the depth first search function, it'll basically be depth first search stack. And the idea here is, again, we have some sort of stack. I just realized that this is slightly wrong. So here we're going to go function. There we go. Depth first search stack. I misspelled function. 1 second. Okay, so now the idea is we have some sort of stack. It has some sort of node. And then we push to the stack. And then we basically say, while there's something in the stack, like we did with the set of cards, we basically say we have some sort of temporary node that we're using. We remove that from the stack and we push in its neighbors here. Okay. So now the next bit will be the breadth first search queue. Now I apologize because we're running out of time and I want to move on to the next thing. I'm not going to talk about this function so much. I was going to show it in the REPL and all that kind of stuff, but with all the technical difficulties, I'm a bit worried about it. Do I have recursing screen? Wait, no, I should be fine. So this is the breadth first search queue. The idea here is that, again, we have a queue, we put elements into it, and that's how we do it. It's the same as the stack case. Okay, so let me quit here. Sorry, write and quit here. And I'm just going to have you guys trust me. Those functions work. I've tested them. As long as we don't have technical difficulties. Again, though, I do understand what those technical difficulties were. So, okay. So what are we going to do next? So the next thing I want to talk about is, how we can extend this to the SIR model, or rather, the infected cases. Like how we can extend this to be information processing on a graph. So I'm going to draw a graph here, and we're going to have like some person over here who has information, and I'm going to color them in red. And then we're going to say that there's a group of other people. We'll just kind of draw them out here. It doesn't really matter how they're drawn. And the point is they're connected in some way, right? So this person is infected. They have information. And what we're modeling here, again, is how that information is spread across the graph. So this person is infected, and assuming that it's just a binary, you infect the people next to you, he'll then go about infecting these people, who will infect these people, and these people, and these people. Now, I do want to show you guys a particular website online that does this pretty well. It's actually done by Nikki Case. You might know Nikki Case. They're a wonderful content creator. So I definitely recommend checking out their stuff. But here's basically the simulation we'll be running. We connect a bunch of people. Again, it doesn't really matter how we connect them. And then maybe we cut that off and put this here. And the idea is the information first spreads to these nodes, then that node, and then this node over here. Again, I have to stress that these are people moving around in some sort of society, right? And so the idea is each connection is basically like, I don't know, some sort of interaction at the grocery store or something like that. In the homework, we'll be modeling things differently. Rather than modeling the information spread on the network, we're going to be modeling basically how people interact to begin with. So we'll be moving people around and dealing with the interactions on that level. So when we're talking about information spreading across a network, there are basically 3 classes of people that we can have here. We can have susceptible people. These are people who can become sick. Infected people. These are people who are already sick. And then recovered people. These are people who were sick at one point and now are no longer sick. So in terms of the information storing and information processing and sending, we typically call S people, susceptible people, people who can pull information. That is to say, they can grab information and bring it into their node. Infected people, on the other hand, are pushing people. So these are people who are pushing the information out. And then recovered people are people who can neither push nor pull. Again, though, in the homework, I think we also will deal with other classes of people. Like, for example, people who are exposed to the virus E, which can both push and pull. They can both send out the virus and receive the virus. And we could probably also deal with reinfection rates, where, for example, people who are recovered can become susceptible again. And those are both interesting side cases that we're not considering here because they're in the homework, and also we'll talk about them in other lectures, and they're in Grant's lecture, which is posted in the link below. Okay, so now what I'm going to do is I'm going to open up another file, and hopefully we're just going to keep going because I've already it's a sunken cost fallacy at this point. So we're going to create a script here. One second, which I'm going to be calling SIR test. Is that the best name for the file? Probably not, but that's what we're calling it. So then the idea here is the first thing we're going to do is create enum int SIR. What this is basically a way for us to tell what S, I, and R are. So the idea is we're setting S to be 0, I to be 1, and R to be 2 for any following subsequent code that we're writing here. I'm, again, including the tree helpers because those are helpful. And then also, I'm going to start creating a mutable struct, very similar to the struct that we had before with the node. The idea here, the only difference between the node structure we had before is that we have an additional SIR here, which again corresponds to whether the person can accept or not accept information. Okay, so now we have function infect. This is where things can get pretty tricky. And again, I realize I'm going over, so I'm going through this kind of quickly. The idea here is we take any person, and the idea is if the person is susceptible, that is, they are S in the SIR, then we're just going to change them to infected, and we're going to say for all the neighbors in our neighbors, we're going to infect those neighbors as well. Basically, if you're recovered or you're infected, you cannot become infected again. Now, again, those are things that we'll talk about later, but just for the purposes of information spreading, this is typically what's done. And then from here, what we're going to do is we're going to create a very quick function that just does a SIR test, and we create basically a group of people, which are people who are all susceptible to the virus, and we have 6 of them. For fun, I went ahead and set person 4 to be already recovered so that they can't get the virus anymore. And then I basically created all the graph nodes here. So I said person 1 is connected to 2 and 3, 2 is connected to 3, 3 is connected to 4 and 5, 5 is connected to 6. Basically recreating that graph that you saw before on Nikki Case's website. I then infect person 1. And the idea is after they're infected, they're going to infect their neighbors and infect their neighbors after that. So I'm now going to write this, and we're going to try doing that really quick. So let me go over here, and let's go. So if I do include, I should be able to include, what did I call it? I called it SIR test. I knew I was going to forget that name. So now we have SIR test ready to go. It's a dumb name for a function, but it is what it is. And now we're going to do tree is going to be equal to SIR test here. And what you'll see here is that we have an infection status true, 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 false, true, true. And again, that makes sense. Everyone on the graph was susceptible to the virus, except for person number 4, which was already recovered. Therefore, they can't get the virus again, just based on the model that we're using here. So I can also do a graph plot, I believe, of tree. And I'm just going to do the first element here. And this will show the exact graph that we're working with. Okay. So I guess it does take a second because I had to open Julia and close it up again. But yeah. So far, I think we've gone through most of the information we needed to cover. The very next thing we're going to have to cover here, or I would like to cover here, is a quick discussion on other ways in which we could create this graph. So here again is that graph. Let me just do this. So here you can see we have, let's see, we have 1, 2, 3, 4, 5, and 6. And again, this was the guy who was already recovered, so they didn't get any information. I wanted to create like a cooler animation, but I was kind of stressed for time, so I ended up not quite doing that. Okay, so now the next thing I want to talk about very quickly is a discussion about light graphs, which is a way to create graphs in Julia without as much stress, you could say. So I'm going to go to this guy. One second. Okay, so I'm going to go here, I believe. And then we're going to show you how to do that with light graphs. It's going to be very similar to the previous script that I just had. So again, we're going to use light graphs, use tree helpers, in SIR, all this kind of stuff. The only big difference is that the mutable struct person no longer has other people inside of it. The idea with this is we're using some sort of additional library coming from light graphs to deal with the graph itself. And it's just going to be moving integers around. And the integers are going to correspond to a separate array where we're holding all of the people. This means that our function to infect people is going to be a little bit more complicated, but it's not so much worse. Here, we just infect people. We have both people, the graph, and then the infection point, the point where we're starting to traverse the graph, all in this one function. There we say if people.infectionPoint.SIR is equal to s, we then set, I have this additional isInfected thing in here. Let me go ahead and fix that right now. Okay. Oh no, wait, I think I wanted that. I don't know why I have an extra isInfected thing here. I don't think we need it, but at this point, let's just go with it. Okay. So now we have this idea to infect, and it follows similar logic. If you're actually using the light graphs project like for your own use, probably you'll have a better way to write this function, and that's totally fair. But for the purposes of this particular lecture, we're just going to roll with what we have. Okay, so then we have the function SIR test, again, sir test, and we're going to have people is equal to person s for 1 to 6, like we did before. The advantage here with light graphs is that when we're adding these edges in here, it's actually a very simple just add edge function. And it becomes kind of nice. And then also simple graph here. So we're just going to infect the person and do basically the same thing we did before. So let's go ahead and write this. And now I'm going to move back over here and run that in Julia. So let's do include, and I think I called it light graphs sir test Julia. Okay, that's good. We're almost done. And then, yeah. So once this runs, again, I had to precompile everything because I had to turn Julia off and on again. So it will take just a second. I can then basically run tree is going to be equal to, I guess, sir test again, because, you know, wonderful naming conventions there. And we should see, again, we see the same thing we saw before, true, 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 false, true, true. And if we run graph plot on the tree, we'll get basically the same graph we had before. Okay, that was most of what I wanted to cover today. There was a little bit more detail here and there that I wanted to talk about, but I did have a lot of technical difficulties, so I kind of went through that. I kind of tried to go through those a bit as they came up. So I think I know what this problem is as well, but also not going to worry about it too much. The point is that when it comes to information spreading across a network, there's a whole bunch of different models to spread information across the network. And this is actually useful for a number of different reasons, right? Like, for example, let's say that these aren't people, but these are compute nodes or something like that. And we say job A, or let's say job B over here, can't start until job A over here is done. Well, in that case, you need to spread that information over to, you know, all of the nodes, so that you know you can start the next process or something like that. So there's a lot of ways in which you can use this kind of tree traversal scheme to do a bunch of different things. Not only the epidemic model like we showed, but also you can do a forest fire algorithm. You can do rumor mongering or gossip spreading where you have a single person spreading rumors around. The point is there's a lot to this. And I think it's actually a really cool method that I'm hoping, if nothing else, we showed you why it was cool, even if there were some technical difficulties to go along the way. But that's okay. That's just the nature of trying to do complex things like this. Anyway, guys, that I think will wrap it up for now. I am about 8 to 10 minutes over, so I do apologize for that. But hopefully it was still fun, and I will see you guys sometime later. Bye, guys.